Welcome. In this video I wanted to talk about the example we did in class. I'd like to explain it a little better. So in this example we have 0.05 kilograms of ice, which is at minus 30 degrees, and this ice is placed into thermal contact with 0.4 kilograms of water, and this water is at 35 degrees. And we're told that this is well insulated, which means there is no energy or heat lost to the environment. So whatever is lost and gained must be all maintained or contained between the ice and the water. Since we know that the water has a higher temperature of 35 degrees, we do expect that the water will lose some energy, and that energy lost by the water, all of it will be gained by the ice. So none of it will be lost to the environment. That is the key of the well-insulated container. So let's consider this picture. We know that because this guy, the water is going to lose energy, its temperature is going to drop from 35 to something else. That something else will be less than 35. That's very critical. You do not lose energy and end up with a higher temperature than what you started with. And because we say all the energy lost by the water will go to the ice, that means the ice will have an increase in temperature. But then, when these guys are left into thermal contact, they will eventually arrive at some common temperature when they reach thermal equilibrium. What we do know is that the final temperature they will reach is going to be between 35 degrees Celsius and minus 30. So that is, it must be less than 35, but also it must be larger than minus 30. That's very, very important. We don't know what the temperature is. We're going to designate it by TF, but what we do know, and we can assert, is that that final temperature will be less than 35 degrees Celsius, but it will be larger than minus 30. But notice, in between these two temperature points, we know there is a particular temperature where water or ice undergoes a phase transition. Let's put these temperatures in a number line. For now, discard this bottom part of the screen. Let's come to the number line. We know that the water was initially at 35, and we know that the ice was initially at minus 30. So when we put them into thermal contact, we know the water's temperature is going to drop, and the ice temperature is going to rise. But where will they thermalize at? Where will their final temperature be? Will it be to the left of the zero or to the right? Another way of saying it is, do we expect the water to freeze and become ice? Or do we expect the ice to melt and become water? So we have to make a pick. Is our final temperature going to be on the right side of the 0 point, or will it be on the left side of the 0 point? And 0 point here I mean freezing or melting point. So let's go ahead and use a bit of intuition and experience. How much ice do we have? We have 0.4 kilograms of ice, we have 0.4 kilograms of water, and ice we have 0.05 kilograms. So one might imagine that it is likely that the water has so much energy that it will melt the ice and the ice will become water. So a very reasonable assumption could be that actually the final temperature will be to the right. In other words, the ice is going to go from minus 30, get to 0, and then melt and then increase its temperature, but now as water. So we can take this assumption that the final temperature is going to be somewhere in this region. So let's make this assumption. Now let's capture what are the results of this assumption. Since we said that the ice is going to, we said that the final temperature is going to be on this side, on the right side of that 0 point, we expect that the ice must first go from minus 30 all the way to 0, and at 0 it must melt, and After melting, it must go to another new temperature, the TF, that that final temperature where we have thermal equilibrium. Let's write that down mathematically. So we're going to have heat, which takes us from minus 30 to the 0 point for ice. And here I have used the red color to indicate properties of the ice. And the blue are going to be properties or quantities related to the water. So ice will go from minus 30 degrees all the way to 0. And at 0, the ice will melt. Why does it melt? Well, that's based on our assumption. We said that the final temperature is going to be between 0 and 35. So the ice, in order for the final temperature to be there, that means the ice must melt. So this term is the heat of fusion for ice. I've used multiple subscripts here just to clarify things. Once the ice is melted, it must rise or raise its temperature to the final TF. That we capture by this heat. But it must be clear that when we go from 0 to the final temperature, what was ice is no longer ice here. This is now melted ice. It's now water. Please remember that this term here, I'll highlight it again when we come to dealing with it. Now, the blue part here signifies the part in this mixture which was, to begin with, water. Where did our water start? It started at a temperature point of 35 degrees. And it loses energy and acquires a new temperature, which we call TF, because it's going to be common to both what was initially ice and to what was initially water. So we know our ice is going to go from 35 degrees to some final temperature, TF, and that's what we're looking for. Now, remember the energy gained by the ice must come from the energy lost by the water. So if we add up the gains and the losses, we must come up with a 0. In other words, we're not losing energy to the environment. All that is lost by the water goes to the ice. So if we were to add the gains and the losses, we're going to get 0. Well, if we carry out the mathematical execution of this, we will find that this term, the first term, looks like this. That is the mass of the ice times the specific heat capacity of the ice times the temperature change in going from minus 30 to 0. And this term is the term for the mass of the ice melting. Remember, we have assumed implicitly, we have made this assumption that the ice is what melts. It's not the water that freezes. So this term corresponds to the energy associated with melting the ice. But now, here we have the term associated with the heat necessary to get the now melted ice from 0 to TF. So that's why here we have the mass of the ice, but the specific heat capacity is no longer of the ice because now the ice is melted. That's very, very important. It's CW, it's the specific heat capacity of water. And the temperature change is the one from 0 to our new final temperature, TF. And obviously, this blue part corresponds to the mass of that which was initially water when we began with this experiment, times the specific heat capacity of the water, times the temperature change in going from 35 to our new final temperature, TF. And if you unpack, you plug in the values, this is what things look like. You're welcome to pause the video and look at it thoroughly, or you could work it out yourself and compare. The key, the takeaway point here is that we know what MI is. It's the mass of the ice. We know what CI is. It's something we could look up in a table. And LF, we also know. CW, we also know. The only thing we don't know are these two TFs, the final temperatures. So these are our unknown. So we could take a common factor, group these two terms, and take a common factor. If we group them, we're going to end up with this on the one side and take everything that has no TF to the right side of the equation. And that's what this is going to look like. And just to save time and for the brevity of the video, I have gone ahead and calculated what the outcome of TF is. What you will find is that T final is going to be 20.58. And notice, remember, we have implicitly made the assumption that the T final will be between 0 and 35. Well, look at this. 20 fits the bill. 20.58 is larger than 0 and it's less than 35. So this fits the bill. You might say, well, how did I know this assumption? What if maybe my intuition was wrong? Well, let's try it the other way. Let's make the assumption that it is not the ice that will melt and become water, but let's assume it is the water that will freeze. Let's try it out. Okay. If we assume that it's the water that will freeze, that means our final temperature TF, our final thermal temperature at thermal equilibrium, must be between -30 and 0 degrees Celsius. Because remember, the ice is going to absorb energy from the water, so it's going to increase its temperature a little. But then the water is going to lose all of its energy and freeze, and this is by assumption. We have made this assumption. So let's consider, what will the water undergo? The water will first go from 35 degrees down to 0. Because 0 is a special point for water, at that point we will need to change phase. So this term QFW is the heat of fusion for water. But then again, because we assume that the water freezes, we know that we must go from 0 to another point TF, to the final temperature TF. So these three terms correspond to the processes that water will undergo when it freezes. But what will happen to the ice? Because the ice is absorbing energy from the water, its temperature will go from -30 to TF. But remember, we have assumed that TF is here, so the ice will not freeze because TF is on the left side of the 0 point. Okay, I hope that's clear. But then, again, the sum of the loss plus the sum of the gain, the total losses plus the gains, are always equal to 0 when the system is insulated. Again, we were told that this experiment is conducted in a container that doesn't interact with the environment. Okay, let's continue now and unpack what it all means. Water going from 35 to 0, this is how much heat it will lose in being converted or phase transitioning from liquid to solid. This is the amount of energy that will be associated with that. But now, once the water has frozen, its specific heat capacity is no longer CW, but it's CI for ice. Now the water frozen will go from 0 degrees, which is the freezing point, to the new final temperature, the thermal equilibrium point. So that's what the water will undergo. Now let's consider the ice. Well, the ice, we know we have by assumption determined that the ice will not melt, so it won't undergo phase transition. So the ice will go from -30 to T final. So our final temperature is TF minus -30. And if you were again to make TF the subject of the formula, because we know all of these other terms, these terms are available, it's data given to us. The only thing we don't know is TF. If we were to solve for TF, we would first have to take a common factor, take TF as a common factor between this term and that term, and take everything else that doesn't have TF to the right side of the equation. Now, if we were to do that, this is what our equation will look like. And again, for brevity of the video, I have gone ahead and calculated what the TF, what value of TF would we gain. The value we would obtain by assuming that the water is the one that freezes is that the final temperature is going to be minus 83. This is contradictory to what we observe in nature. The final temperature, the final temperature where the system comes to thermal equilibrium is always between the two starting temperatures. Where would minus 83 lie in this number line? Minus 83 will lie outside of that interval, somewhere here. It's not in between what we started with. So the claim here is that the ice, when you put it in contact with something hot, it would lose energy, hence its temperature would drop even more, and that's not true. So this means our assumption that the water freezes must be wrong. So actually, it's not only our intuition that helps us here, but even the mathematics will tell us that our assumption would be wrong in this case. So this is one very detailed way of showing you why the temperature of the final temperature, the thermal equilibrium, will be 20. Hence, the ice is the one that's going to melt and not the water freezing. Okay, if you have any more questions about this, you're welcome to let me know. Post it in a comment, and I'll see you guys in the next one.